Hi everyone, welcome back to our computer science lesson. In today's video, we are diving into number systems part 2. And at the end of this lesson, you should be able to understand how and why hexadecimal is used for data representation. You should be able to understand how to do addition of two positive 8-bit numbers. Also, you should understand the concept of overflow and two's complement. Okay, so let's start with why hexadecimal system is used. Now, we already know that computers understand binary, which is ones and zeros. But imagine that you're trying to read or write a really long binary number like this. Okay, this is very long and it's a bit confusing. It's confusing and difficult to remember. But then we have hexadecimal. So one hexadecimal digit stands for 4 binary digits, which makes it shorter and easier to read for humans. So instead of writing all of this binary number, we can just use this 4 digits to write the binary numbers. So although computer scientists understand binary, but they find it more easier and convenient to use hexadecimal because it is easier to remember and it is shorter. Okay, now the uses of hexadecimal system. We have 4 usage. The first one is error codes. If you have ever seen a message like this, okay, this type of message is a hexadecimal code. These developers use this to understand what's going wrong in software or a website. So when a programmer or a developer sees this error code, they know the exact problem with the computer system. So every programmer or developer must be able to interpret the hexadecimal codes. Usage 2. Access control. Okay, media access control. Usage 2. Media access control, which is MAC addresses. So MAC address is a unique identifier of a device on a network. So MAC addresses are written in hexadecimal and it looks like this. So the first part of the MAC address helps us to identify the manufacturer of the device, and the second part of the device helps us to identify the device ID. Usage 2. Media access control, which is MAC addresses. So MAC address is an address that is given to a device on a network. So it is used to uniquely identify a device on a network, and it is written in hexadecimal. So here is an example of a MAC address. So a MAC address, the first part of this MAC address tells us the manufacturer of the device, while the second part of the MAC address tells us the device ID. Usage 3. Internet protocol, which is IP address. So IP address are also written using hexadecimal, and the reason why it is used is to make the IP address more compact and readable. Okay, so basically it reduces the length of the address compared to if the address is in binary format. Okay, the last usage 4, HTML color codes. So if you have ever designed a web page or you're a web developer, you would know that the color code is written using hexadecimal. So for example, if you want to represent an orange color, so this is the orange color in hexadecimal. Okay, and each pair, okay, the first pair is RR, which is red, then green, then blue. So these are the usage of hexadecimal system. Okay, now let's go to addition of binary numbers. So in computer science, we in computer we also do addition. So how does computer do addition in the system? Similar to doing addition in math, we have the concept of the sum value and the carryover. For example, when we have something like this, 19 plus 23. So 9 plus 3 is 12. So we write down 12, which will be the sum, and then we carry over 1. Okay, same concept in addition of binary numbers. So here are what you should take note of when doing addition of binary, because we only have ones and 0. So for easy memorization, we know that 0 plus 1 is 1, or 0 plus 0 plus 1, or 1 plus 0, whichever way. Okay, it means 1. When you have 1 plus 1, okay, 1 plus 1 gives us 1 0. And then when you have 1 plus 1 plus 1, we have 1 1. These are the three you need to take note of. Anything 0 0 0 plus 1, you will always have 1. 1 plus 1, let's use this example. 1 plus 1, you have 1 0. 1 plus 1 plus 1, you have 1 1. So for example, if we need to have 1 0 1 plus 1 1 1, okay, 0 plus 1 is 1. 1 plus 1 is 1 0. So we write 0, we carry 1. 1 plus 0 plus 1 is 1 0. We write 0, we carry 1. 1 plus 1 plus 1 is 1 1. So we write 1, we carry 1. And then we write the number we carried. So that is how to do addition of binary numbers. Now let's look at some examples. Okay, so we need to add these two binary digits together. 1 plus 1 is 1. 1 plus 1 plus 0 is 1. 1 plus 1 is 1 0. So we write down 0, we carry 1. 1 plus 1 plus 0 is 1 0. We write down 0, we carry 1. 1 plus 0 plus 1, 1 0. Write 0, carry 1. 1 plus 0 plus 0 is 1, then 1 1 0. Example 2. So we need to convert 126 to and 62 into binary. Okay, if you don't know how to do the conversion, you can refer to number system part 1 video. Okay, so now we have these binary digits and we need to do the addition. Okay, let's go. 0 plus 0 is 0. 1 plus 1 is 1 0. So we write down 0, we carry 1. 1 plus 1 plus 1, we have 1 1. 1 carry 1. 1 carry 1. 1 carry 1. 1 carry 1. And then we have 1 0. So 0 carry 1 and then 1. So if we want to be sure that our answer is correct, just say 126 plus 62, we have 188. So we can find the binary of 188. So we can use 1, 2, 4, 8, 16, 32, 64, 128. Okay, so 188 minus 128, 0, 6. So here 1. Okay, 60 is less than 64, 0. Then we can have 32, that's 28. We can have 16, so 16, and then we can have 8, we can have 4, and then we have 0, 0. Okay, we can see that our answer is the same. Okay, now let's look at the concept overflow. First, let's do the addition of the binary digits using 8 bits. Okay, so I'm just going to write it here, 110, 1110. And then we have 110, 11110. Okay, 0, 0 carry 1, 1 carry 1, 1 carry 1, 0 carry 1, 0 carry 1, 1 carry 1, 0 carry 1. Now, if we look at the answer properly, we would see that something is not right. Okay, we can, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, you'd see that we have 9 bits. And remember, the question says using 8 bits. So an overflow has occurred. What does this mean? It means that a ninth bit has been generated. This error is called overflow. And then how do we write that in exam? Okay, basically you just need to state that an overflow error has occurred. Okay, and this means that the number is too big to be stored in the computer using 8 bits register. Basically, it's like you have a container and the container can only accommodate 500 ml, and you're pouring in more than 500 ml into the container. So what will happen is there's going to be an overflow. So some liquid will be wasted. Okay, so that is what overflow means. Now let's look at the concept logical binary shift. So in computer system, we can also perform multiplication and division. But in the case of logical binary shift, when we multiply, we are multiplying by 2. Okay, and then when we divide, we are dividing by 2. So when we shift the binary to the left place, it means multiplication. And when we shift to the right place, it means division. Okay, let's look at an example. So we have this binary number, okay, this binary digits, and it is 7 in denary. So this is the binary number. Now we need to move it one place to the left. So if we move it one place to the left, that means this will be lost. And then this comes here, comes here, comes here, comes here, comes here, comes here, comes here. And then we have an empty box. So the empty box we are going to just replace with 0. And then if you check the value, okay, in denary you would see this is 8, 4, 2, together gives us 14. Okay, so basically the value has been multiplied by 2. And let's try to shift 2 places. Okay, if we shift 2 places, 1 and 2 will be deleted. So we'll have 1, 2, 3, 1, 2, 3, and then we have 1, 1, 1, 1, 1, 1, and then the empty boxes we replace with 0. So if you check, 4, 8, 16 altogether gives us 28. Now, how do we write this mathematically? So you need to, if you want to double check if your answer is correct, you need to say 7 multiply by 2 raised to power the number of times we shifted. So we shifted 2 places, so we are going to have 2. So 7 times 2 raised to power 2 is 4. It gives us 28. So our answer is 28. Now let's look at division. Okay, so we have these binary digits and the denary value is 44. So let's shift 2 places to the right. So if we shift 2 places to the right, that means 2 digits will be deleted. Okay, so when 2 digits is deleted, then this comes here, and then like that. So we have 1 1 0 1 0 0, and these 2 will be empty. So we replace that with 0. Okay, now to check our answer, we have 8, 2, and 1, which gives us 11. Mathematically, how do we check that? We write the denary value divided by 2 raised to power. We shifted 2 times. So 44 divided by 4, our answer will be 11. Okay, now let's look at another example. Okay, so when we are shifting binary digits, there's also a limitation. Okay, especially when we are using 8-bit register. Now look at this denary value, okay, which is this in binary. Now let's shift this value 4 places to the right. If we shift 4 places to the right, that means we're going to lose 1, 2, 3, 4, and then we have 0, this 0, we have this 1, and then we have this 1, and then the empty boxes we replace with 0. Now if we look at the value of this, it is 8 plus 4, it is 12. Now let's check mathematically if that is correct. 200 divided by 2 raised to power 4. 200 divided by 2 raised to power 4 is 16. So we have 12.5. And 12.5 is not the same as 12. So what has happened? We have lost 1 bit, okay, which is this. Okay, 1 bit has been lost. And because that 1 bit has been lost, it has made this value to be incorrect. So what do we say has happened? We say that we have exceeded the maximum number of right shifts possible using 8-bit register. If we're using more than 8-bit register, then it's fine. But using 8-bit register, we cannot shift 4 places. Okay, now let's look at the concept of 2's complement in binary. Now, the same way we are able to represent positive number in the computer is the same way we can also represent negative numbers in binary. And to do that, we use what we call 2's complement. The technique to represent a negative binary number is called 2's complement. Now, the only difference with the heading is with the heading value, okay, and the heading value 128 needs to change. Okay, so 128 needs to change to negative. This is for 8-bit number. Okay, so now when you see, how do you identify a negative number? A negative number will start with the value 1, and a positive will start with the value 0. So that's how you identify negative and positive in 2's complement. Okay, let's take an example. Okay, when we need to convert negative denary number into binary number in 2's complement. So there are 4 steps to do this. The first step is to change the negative number to positive number. So by removing the negative, so this becomes positive. The second step is to find the binary form. The binary form. If you find the binary form, you would get 10000011. but this is 7 bits, so you have to make it 8 bits by adding extra 0. And then the next step is to invert each binary value. How do you invert? You flip. Wherever you see 1, you change to 0. Wherever you see 0, you change to 1. And the last step is to add 1 to the binary number. So just say 1 and then 1 0 1 1 1 1 0 1. So that is the answer. The next example, convert negative binary number into 2's complement format and convert to denary. Okay, so this binary number we need to convert to denary in 2's complement. So all we just need to do is to write the heading value the same way we convert binary to denary. Write the heading value. The only difference is the 128 will be negative. So we have negative 128 plus 16 plus 2 plus 1. And your answer will be negative 109. Okay, the next question. Convert positive denary number to binary number in 2's complement. Okay, this is pretty straightforward also. So this is a positive denary number. The first step is to convert it to binary. Okay, when you convert to binary, you get 100110. Okay, then you just need to add the extra zeros to make it 8 bits. Okay, the extra 0 make it 8 bits. And since it's a positive number, we have to have 0 in the negative 128 column. Okay, another example. Positive binary number in the 2's complement to positive denary number. So this method is also same way as converting binary to denary. Okay, so you need to multiply each binary digit with the heading. Okay, so we have 64 plus 32 plus 8 plus 4 plus 2, and we have 110. Okay, so that's all for this lesson. If you want to understand this lesson even better, watch the video Topical Past Year Questions.